Steinhauer here, welcome back. We'll start today's class with a review question covering the topics we were talking about in the last class. And this one's a tricky one. So I wanted to circle back to it too, because there's a lot going on here and it's important to unpack it and understand what's going on. So here we have an HR diagram, but it's not quite a typical HR diagram in that temperature is the x-axis, and it's still true that the hotter stars are on the left and the cooler stars on the right. But instead of this being luminosity or absolute magnitude, the y-axis here is apparent magnitude. Now, for stars in a cluster, this is okay because if all the stars have the same distance, then a change in luminosity will also be a change in brightness, and brightness will scale with luminosity. But you can compare this to determine which stars are further away, because all of the stars will get brighter or fainter depending on how far or close that cluster is to us. So the two questions that I have are, which of these two clusters is younger? I've got two clusters here, A and B. And again, this is a line, but it's tracing out where the preponderance of the stars are on this color, what's called the color magnitude diagram. So which one of these two clusters do you think, A or B, is the younger cluster? Okay, what is the answer? Well, remember that we can determine the ages of clusters by the main sequence turnoff point. That is the point at which stars are beginning to leave the main sequence, meaning they're running out of hydrogen and moving up into the giant regime. The further up you go to get that turnoff point, the younger the cluster has to be. Because remember, these are the most massive, hottest stars up here that live the shortest lives. A must be a fairly young cluster because these stars still seem to be on the main sequence all the way up at the top. Whereas star B, these stars are already turning off at this point, and this seems to be the main sequence turnoff point right here, which again, you can't really compare brightnesses here because it's apparent magnitude, but you can compare temperatures, right? This turnoff point is way cooler than this turnoff point over here. So B must have aged. All the stars that used to be up here have already evolved off the main sequence and died. And only these are left down here. So B must be the older cluster, which makes A the younger cluster. Okay, review question number 2. Which of these clusters is farther away and why? Okay, remember here we are thinking about the main sequence stars themselves. For instance, if you compare that star right there to that star right there, those two stars are both on the main sequence and have exactly the same temperature. We expect stars of the same temperature on the main sequence will have the same mass and will have basically all the other properties the same as well. So we expect the luminosity of that object to be the same as the luminosity of that object. So we can tell which one of these is closer. If you have two stars of the same luminosity, the one that looks the brightest must be the closest. And so since the main sequence of cluster B is above the main sequence of cluster A, it must be, and therefore brighter, since this is apparent magnitude working in the same way the HR diagram was, meaning that brighter is to the top. The cluster B is brighter at the same temperature, therefore it must be closer. Okay, so in this class, we are going to be talking about, moving on to talk about how stars are formed. And I want to take a very brief foray into chapter 20, which is the interstellar medium, between the stars, gas and dust and space. A very brief foray. I've got 2 slides on this, so don't blink. So you may have heard, and it's pretty much true, that space is a vacuum, but it's not a perfect vacuum. It turns out that there's stuff in between the stars. And it is that stuff that, when it gets in the right conditions, can actually make new stars. Let's talk about the stuff itself first. Here is an example of an image of space, right? And you can see there's stuff there. It's not completely empty. It's not a complete vacuum. And so here is a particularly interesting and dense region of space, but you can see all kinds of interesting things going on, right? Obviously, there are stars in this field, but there are other things as well. You see some bright nebulas over here. Nebula is just a word that means glowy stuff in space, really. And when you see this blue stuff, this is usually dust in interstellar clouds that is reflecting very hot, bright starlight. When you see very diffuse red gas like this, that's usually gas that's been heated up by a very hot, dense object and creating an emission nebula. But also in this image, you see some very dark clouds, some dark regions. These are regions of the interstellar medium where the gas is much denser than it is in other parts of the interstellar medium. And so you can see not only is there stuff between the stars, it's not even uniformly distributed. It's clumpy. There are regions where there's a lot more of it than others, kind of like clouds, although these aren't water clouds. These are clouds of hydrogen gas and dusty stuff that filters into the interstellar medium from hot stars and things. Okay, how is this stuff distributed through the galaxy, you might ask? Well, again, this isn't the Milky Way, but the Milky Way probably looks similar to this. This is the Andromeda galaxy. And you can see the different regions of the interstellar medium in the Andromeda galaxy itself. And you can see the different parts. So for instance, this diffuse sort of blue glow here is the diffuse neutral hydrogen gas. This is sort of the pervasive stuff that is between the stars in a typical galaxy. The weird stuff is sometimes you get these pink regions. That is regions usually of star formation where you've got stars that have just been formed that are still embedded in their molecular, the clouds that they were formed in. And they're so hot that they're causing the atoms in their immediate vicinity to become excited and glow as an emission nebula. These things usually look pink. We call them H2 regions sometimes because H is hydrogen and 2 stands for ionized hydrogen, meaning that it's lost an electron. When it regains that electron, it glows in this characteristic pink color. And this is how you can notice this particular type of region in the interstellar medium. But you also have these very dark bands, right? And these are regions of the interstellar medium. So these H2 regions are very hot regions of the interstellar medium. These dark regions are very cool and dense regions of the interstellar medium. They're so cool, in fact, that molecules can begin to form. And so instead of having just single hydrogen atoms sitting out there, you might get hydrogen molecules where you get 2 of them bonded together with a molecular bond. And it takes much cooler temperatures in order to get those kinds of things happening. And that happens in these very dark, dense regions of the interstellar medium. So that's a typical galaxy, and you can see the different regions of the interstellar medium in this one picture. Okay, that's pretty much all I want to say about the interstellar medium. We'll touch on some other things in the interstellar medium as we go, but I want to move right on to the more interesting part of the interstellar medium, which is where those stars are actually happening and how we actually can form stars in the universe. And that's the subject of chapter 21. Okay, so let's get to it. How do and why do stars form? Basically, it's actually, believe it or not, kind of hard to form stars in the interstellar medium. You need a couple of things to happen. You have gravity, which is trying to pull things together, and you have pressure, which is trying to push things apart. You need gravity to beat pressure in order to have a star form and collapse into a star. If you start off with a large, dense cloud, you need it to collapse into a star. You need gravity to win that battle. And so you need a place where the gravitational force is going to beat the pressure force. And so since the pressure gets stronger, the hotter you get, the best places to form stars are the places where the force of gravity is the highest. And those are places where it's very dense, where there's a lot of matter there. So dense regions, which means high gravity. And you also need very cool regions, very cold regions. because the colder the gas is, the smaller the pressure will be, and the more likely it is that gravity will be able to overcome. So if you have a gas that's sitting there that is dense and cold, you have a chance to have gravity beat pressure and actually have this thing collapse and form a star. Here are some pictures. So where do they form? Here is an example of such a thing. This is an image of a cold, one of these cold, dark molecular clouds. Those molecular clouds that we saw are the coldest and the densest regions of the interstellar medium. This is a spot in the interstellar medium where we expect stars will be forming. And in fact, we can see stars actually being formed in these particular regions. Here's an example of what looks like just a random star field. And you can't even really tell if there's something interesting going on. But it turns out that there is a very dark cloud that's right here. And in the visible part of the spectrum, you can only tell it's there because it looks like there should be stars here that are not. It's blocking out the view of the stars that are behind this cloud. So it turns out, though, that in certain wavelengths of light, it's easier to see through these clouds. In fact, dust is very notoriously good at blocking out blue light, but progressively worse and worse and worse at absorbing redder and redder and redder light. And so if you look at this same region in the infrared instead of the visible, it looks completely different. I'm going to go back and forth between these two pictures, and I'm going to try to convince you that they're the same region, even though it might not look like it at first. So here is one, and here is the next. These are the same region. Let me try to prove it to you. Look at this star and this star and this star. That's this star and this star and this star. Those are exactly the same stars. This one, this one, this one is this one, this one, this one. We're just seeing this in the infrared. And in the infrared, light travels much easier through these dusty particles. You can actually see embedded in that dark cloud is this very, very red, because and so it's very cool object that is in fact a baby star, still embedded in the molecular cloud from which it formed. And so infrared light can, if you want to study in star formation, if you want to study how stars form in their natural environment, visible light is a very bad place to do this because it's invisible. But if you use infrared light, you can penetrate through the dust and see objects that are embedded in these very dark, dense molecular clouds. Let's think about how this works a little bit, because this is kind of important. Dust in the interstellar medium absorbs light as it passes through it. And the more dust there is, and the denser the region, the faster it absorbs that light. But it doesn't absorb all of the light at the same rate. In fact, it's much more efficient, dust is, at scattering blue light than it is scattering red light. And this leads to an effect called interstellar reddening. So if you're looking at a star through one of these dust clouds, some of that light will be absorbed, but more of the blue light, or reflected or scattered, but more of the blue light will be scattered than the red light. And so that causes stars to look redder than they should. In fact, you can kind of see this. If we go back, some of these stars that are at the very edge of this nebula, of this cloud, look redder than they should. Why is that? Because the light is passing through a lot of this dust, and the blue light's getting scattered away, and it's only the red light that's available to us when it reaches us here on Earth. So we have to take this into account. Sometimes you can't trust the color of a star, especially if it's passed through a lot of this interstellar medium stuff along the way. Okay, you actually have some familiarity with this phenomenon. We see it every day on Earth. This is in fact the reason why the sky looks blue, right? Because starlight that is traveling, sunlight that's traveling from the sun, as it travels through the sky, it interacts with these dust particles, and the dust particles scatter those blue light photons preferentially to the red ones. So when we look up at the sky, we're seeing that only the scattered light. and that's why the sky looks blue. It's also the same reason why the setting sun looks very red or very orange. It's because that sunlight has passed through a lot of this dust on its way towards us. And as it does, it's absorbed some of that light and the blue light preferentially, leaving behind only the red stuff. And so that's why sunsets are red and also why the sky is blue. It's because of the dust in the atmosphere scattering the blue light preferentially to the red light. Here's another example of a region in space where stars are being formed. I'll maybe post a video on what this looks like in real life and its transformation from a visible spectrum to an infrared spectrum. Again, you can see regions that are denser here in one spectral region, looking like there are stars actually being formed in that region in another spectral region. This is why it's important to study the universe in multiple wavelength regimes. We get completely different information about these astronomical objects at different wavelength regimes. In fact, the infrared sky is way different than the visible sky. This is a familiar constellation. We've shown an image of this constellation a lot in this class. This is the region of Orion. Here is the bright star Betelgeuse. The three belt stars, you can't even really see them, but they're here. And the Orion Nebula is just below it right there. If you had eyes that were visible, that could detect infrared light, you would see this entire region of the sky glowing because it is a giant star formation complex. There is lots and lots of what used to be dense molecular clouds that have formed stars. Those stars have heated up the gas, and that gas is now glowing in the infrared. Okay, I'll end this video with a suggestion to watch one of the videos that I'm going to post in the supplemental videos below. And that is this video of a simulation of star formation. What they did was start with a spherically symmetric cloud, perfectly uniform density, and 50 solar masses worth of stuff there. And they tweaked it a little bit. They introduced some random motion so that it wasn't perfectly uniform. And then they just let it go. They turned the physics on and they let it go. And what you're going to see happen is you might think that the cartoon version of star formation is that the whole thing collapses down into the center and forms a star immediately. That's actually not what happens. There's all kinds of other forces at play, including pressure and angular momentum forces, that causes this cloud to fragment and form lots and lots and lots of different smaller stars. And so watch the video. It's kind of fascinating. It will zoom in and change the scale, and you'll follow some of the very most massive stars in the center as they're formed, and watch other stars as they're formed get kicked out by these larger stars. And at the end, it'll zoom out and you'll see a situation that looks kind of like the star forming regions that we've seen before. Lots of hot gas that's still tenuous and moving around, and lots of stars embedded within it and also around it that were formed in the process. But the point is, this is not a cartoon version where everything just collapses to the center. It's a very chaotic and turbulent and difficult to understand process without actually using the simulations like this. Okay, we'll come back and talk more about this on the next video.